term. These are undirected polymers, and there's also no random environment. So, and it turns out that for us it will be convenient to take a continuous time parameterization for these polymers, and they're on ZD. So let x of t be a simple random walk, and I always assume that walks start at the origin. Then you can then the intersection local time is the amount of time that a walk spends intersecting itself, and it's given by this double integral. And you can also write it as the square of the L2 norm of the local time, where the local time is the time that the walk spends at a certain site up to a given time t here. And given this local time, there is a natural measure on polymers, on walks that you can define, which is given by this kind of Boltzmann type weight with respect to the simple random walk, which reweights every path by this exponential factor e to the minus g I of t being the intersection local time. Here, g is a positive parameter. And in principle, you could do all the same what I just did, and just as well in discrete time. And when you do this in discrete time, you can take this parameter g to infinity, and what you obtain is the uniform measure on path on the lattice that do not intersect itself, also known as the strictly self-voiding walk. In continuous time, you have to be a little bit more careful, but there's also a way to make sense of this limit g goes to infinity. However, all that I'll be talking about in the later half of this talk will be for small g. However, there's a kind of universality conjecture which states that the behavior, or the long-time behavior of these walks is supposed to be independent of this parameter g, no matter what it is, including the strictly self-voiding walk. So as soon as g is positive, all these measures are supposed to behave the same. What are the kind of questions we'd like to know? Well, the most natural question you might ask is, how far is the endpoint typically away from the point you started with? So the so-called end-to-end distance. It turns out, as often in statistical mechanics, that it can be useful to study, so there's a numerator and a denominator here, to study numerator and denominator separately. And the normalization, which I denote by z sub t, is the normalization, and the unnormalized endpoint distribution is the so-called, is denoted z sub t of x. And it turns out that it's useful in this case to take Laplace transform in this time or length parameter t. And these Laplace transforms are known as the susceptibility and the two-point function. Now, if you want to learn something from these Laplace transforms about the original sequences, then, or the asymptotic behavior of the original sequences, then you need to understand how the Laplace transforms behave in the vicinity of their radius of convergence. And so the existence of the radius of convergence, or that there is a radius of convergence, is more or less a triviality in this case, at least for the susceptibility. These normalization constants z sub t are submultiplicative, basically by cutting walks. And as a consequence, there's an exponential growth rate, which I'll denote by nu sub c. It depends on the parameter g. So this nu sub t is, of course, then also the radius of convergence of the susceptibility. And it turns out it's actually also the radius of convergence of the two-point function for any x, but I won't need this. So what's known? If you look at dimension 1, at least the strictly self-voiding walk is kind of trivial. It either goes left or right and behaves ballistically. Turns out this is also the case for the weakly self-voiding walk. It's not a triviality in that case, but it's known that it also behaves ballistically for any positive parameter g. For dimensions 5 and more, on the other hand, the self-voiding walk behaves diffusively, again, for weakly and strictly self-voiding walk. This is known in the sense that the squared end-to-end distance grows like t, that the susceptibility at the critical point blows up like epsilon inverse, and that the two-point function at the critical point decays like the simple random walk two-point function. For dimensions 2, 3, and 4, the situation is believed to be different. Self-voiding walks supposed to be super diffusive and subballistic. The best bounds known are these. There's a lower bound and an upper bound. The lower bound, well, sorry? Yeah.
So in 5 dimensions, can you let the G be arbitrary, or is the result for small G and one G equals infinity? Or
more or less, but I think it's believed that you could also take G arbitrary. So really the results are, so the dimension, or the 1 over the dimension can be seen as a small parameter, alternatively, if you want to study strictly self-voiding walks. And so initial results in that regime were for a very high dimension, and this dimension was lower to dimension 5. So you're right, it's not done for large values of G, but presumably this should be possible somehow. So these are the best bounds known. Unfortunately, they're rather far from the truth, or what we believe is the truth. The lower bound doesn't even show that self-voiding walks grow as fast as the simple random walk, but it's believed to grow much faster. On the other hand, the upper bound does say that self-voiding walks are subballistic, but in a quite weak sense. For example, they're not sufficient to lower this growth exponent by a small epsilon.
In 4 dimensions, do you expect different power or just
Logarithmic
logarithmic corrections?
corrections. I'll say something about this in just a second. So on the other hand, dimensions 2 and 4, at least, there's very precise predictions. In dimension 2, there's these explicitly conjectured exponents, and there's been some major mathematical progress due to the invention of the Schramm-Loewner evolution that gave some independent confirmation of these exponents, but proofs are not known. In dimension 4, on the other hand, we expect logarithmic corrections to the behavior of the simple random walk. So the end-to-end, or the squared end-to-end distance is expected to grow like t log t to a quarter. The susceptibility is expected to blow up like epsilon inverse times log epsilon to a quarter. And the 2-point function is expected to have the same decay as the simple random walk 2-point function. So there's no logarithmic corrections for the 2-point function. So yeah.
If you take several random walks in 4 dimensions for linear motion, we know that they don't never encounter each other, and that's probably true here too.
Yeah, I'll actually say a little bit about that in just a second. The work I'd like to talk about is a confirmation of this blow-up of the susceptibility for very small interaction parameter G with this correction log epsilon to the 1/4. As I mentioned at the beginning of the talk, this relies heavily on independent work of Brydges and Slade, who studied the 2-point function at the critical point and can show that it behaves like the simple random walk 2-point function, so no logarithmic corrections. And in fact, it's already known for a long time that if the 2-point function decays like the simple random walk 2-point function, then there can be at most a logarithmic correction for the susceptibility. But there is one. So in particular, we know 2 of these quantities. There's heuristic arguments which are related to the 3rd quantity, but we can't make use of this. This is not well. This is not trivial. So let me mention a few other related results, which are in particular work by Brydges, Evans, and John Imbrie, and by Brydges and Imbrie, who studied a hierarchical version of this model, and they have rather complete results, including the end-to-end distance, so including the distance between the origin and the endpoint, and they can show that it behaves like it's also predicted to behave on the Euclidean lattice. There's work by Hara and Tazaki, who used the method of Gewetsky and Kupiainen to find similar logarithmic corrections for the phi-4 model. This is closely related, as I'll say in a few minutes. And there's also work by Lawler on the loop-erased random walk. The loop-erased random walk is a different model of self-voiding walks. It's in a different universality class, if you like. So the exponents are different, but well, in 4 dimensions, it also behaves, well, it also has logarithmic corrections to the behavior of the simple random walk. And there's also results on decays of 2-point functions, various models, and so on. Let me not spend too much time on this. Let me say a few words about the criticality of 4 dimensions. If you consider a kind of toy model where you take 2 independent simple random walks and ask how often do they intersect, then you'll find by an explicit calculation that this is infinitely often in dimension 4 and lower, and finitely often in dimension 5 and more. More precisely, you could add a little killing rate, m squared, to each of the walks and ask how does this expected intersection time with killing rate diverge as the killing rate tends to 0. And of course, it's bounded in 4 and more and 5 and more dimensions, and it diverges logarithmically in 4 dimensions and faster in lower dimensions. And so this expected intersection time is also known as the bubble diagram. And in fact, the finiteness of the bubble diagram, as many of you are experts, is a key input or is a key ingredient in improving the behavior of this self-voiding walk in 5 and more dimensions. On the other hand, this logarithm here that appears here turns out to be actually the same logarithm that appears here. So at the end, it'll come in right exactly because of the logarithm in this bubble diagram.
Would you go back to the
Yeah.
bubble diagram? Shows you the proper walk?
Well, it doesn't show the power. But no, it doesn't show the power. But it'll in some complicated way, it will be exactly the bubble diagram that gives rise to the logarithm for us.
You can't get the power.
No. Yeah. Okay. So much for that. Now let me say a little bit about how this is proved. This relies on a kind of a supersymmetric structure of the model. Let me recall a few facts that many of you know very well. So first of all, if you take a matrix, say on a finite dimensional vector space that has a positive definite real part, then you can write its inverse as the covariance of a Gaussian measure, of course, and here I wrote it as a complex Gaussian. For many purposes, this normalization factor, the determinant in front, is an inconvenient feature. And one way to at least to kind of formally get rid of it is to lift the exponentials into the exponent, as on the second line. So by this I mean view them as differential forms. Then you can write this. You can write this expression, which is to be interpreted as expanding out the differential form part. And what you obtain at the end is a differential form. And if you remember your calculus course, then differential forms make sense to integrate if they have top degree. So you only integrate the top degree here. And this is the same. So nothing has happened. But the determinant has disappeared. Also, while the first line only made sense to integrate for ordinary random variables, or differential forms of degree 0, if you like, the second expression has a meaningful interpretation in terms of any differential forms by simply multiplying the differential form by this integrand and then integrating the top degree part. Different way to see this is to define this symbol psi of x as the differential d phi x up to a normalization factor. And then you can write the same formula on the previous slide as this. And this field psi has an interpretation of being an anti-commuting analog of the field phi, a fermionic field, if you like. You look skeptical.
Well, the notation is simply unusual now, because in the old days you would also add a d phi bar, d phi, d.
Well, this is a differential form here, right? So,
But
yeah.
I mean, if you look at the erasing formulae, right?
You can write a d phi if you like, but I think this is a natural way to introduce this for people who haven't heard about Brydges integrals, which seems like a kind of unappealing, may seem as a kind of unappealing concept as first, while this is something everyone has learned in their first or second year calculus courses. Anyway, so these differential forms have an interpretation of an anti-commuting analog of the original field, and differential forms are the analogs of random variables, and they are always polynomial in this differential, or in the psi field, if you like. And then now you can apply this formula to a particular choice of the matrix, and I'm always be looking at a finite torus, so this is a finite dimensional space, and take the discrete Laplace operator plus a random potential. And the random potential I'm taking here is I times a Gaussian. So this is an imaginary potential. Then you can evaluate this. On the other hand, you can write this resolvent in terms of random walks by a kind of Feynman-Cutts formula. And what you obtain is a formula for the two-point function of the weakly self-voiding walk in terms of such a supersymmetric integral. So the left-hand side is the two-point function of the weakly self-voiding walk. And the left-hand side, the right-hand side is this supersymmetric integral from the previous slide. Now this is a kind of a supersymmetric version of the phi-4 spin model, which you can see. So let me spend a little bit of time on this notation. The symbol tau sub delta is simply this term phi, Laplacian phi, plus a corresponding term for the fermion. Tau is the square of this field, basically, and tau squared is the square of this tau with the wedge product again. So if you drop all the psi's, what you have is the usual phi-4 model. And in fact, this connection with spin models is not new. It's very old. It was already realized by de Gennes that if you take an n-component spin model, or say an n-vector model, and formally let the number of components tend to 0, then what you obtain are self-voiding walks in some way. So mathematically, this limit n goes to 0 is not a convenient limit for us. But as was noticed by Parisi, Sorlas, and McCain, this supersymmetric representation is kind of a way to give meaning to this n equal 0 limit by viewing the number of components as 2 minus 2, the fermionic components counting negatively.
Who was the first one to use the Grassmann variables in this context?
Well, I think it were these. These were both 1980 papers. I think they found this independently. Yeah, yeah.
De Gennes used it rather than.
Yeah, de Gennes used the n equals 0 limit. And in fact, this n equals 0 limit is a common way to study this model in the physics literature. So nonetheless, even though this resembles the phi-4 model and in this way, key methods are of course not available because this is not a probability measure anymore. So one of the challenges is to use methods that continue to hold even though this is not a probability measure anymore. Let me just briefly mention that these fermionic variables are kind of an extra complication, but everything basically works if you omit them. So you can also study the phi-4 model with n components. And if you do that, you find that, for example, if you look at the susceptibility, it also has a logarithmic corrections in 4 dimension with this exponent n plus 2 over n plus 8. And then if you formally set n equals 0, this corresponds to the self-voiding walk case, even though you can't, this result for n positive will not, help you to study n equals 0, right? And for the phi-4 model, there's other interesting questions you can study, but let me not go into this. So the next, from now on, it's going to get slightly more technical to say a few words about how we proceed. First of all, let me ignore the fermions for the time being. So just look at a phi-4 model with this density. Then what you can split it into, at least formally, it looks like maybe you should split it into two parts. One is the Gaussian part. One is perturbation, which is the non-Gaussian part. And maybe you could imagine perturbing about this non-Gaussian part, perturbing about the non-Gaussian part about the Gaussian part. But you have to be a little bit careful because, in fact, the critical point we're interested in studying is negative. So first of all, the first factor is not a well-defined Gaussian measure. So instead, what you could do maybe is you could leave a little bit of a mass in the Gaussian and move the rest into the perturbation. So then you have a well-defined Gaussian measure as the first factor. More generally, however, you could also split this kinetic or gradient phi squared term. Right? You could split it into two parts. One stays here. One goes into the perturbation. And once you do that, you can always rescale the field to normalize the factor that appears here to have constant 1 in front of it. So let me do that. I'll introduce another parameter, z0, and a rescaled field, which I'll use a different phi for, which is rescaled. And then I can split this gradient phi squared term that appears again. And here I have this Gaussian with the normalized gradient phi squared term. And here I have this perturbation, which has this general form, which looks like the initial density, except that it has 3 new coupling constants. So this is the most general way to split this density into a Gaussian times a perturbation. And in fact, we're going to proceed in roughly this way, but it will be absolutely crucial to make the split just right. OK, I'll get to that. Let me proceed. So nothing has happened so far. I've just rewritten this density for the phi-4 field. And introduce two extra parameters. Let me go one step further and continue rewriting this expression a little bit until it's in the form I'd like it to be. So this is the first line is just recalled from the previous slide. The density of the phi-4 model written as a Gaussian times a perturbation. Capital Z naught is the perturbation. This other factor is the Gaussian. What we'd like to understand something about this measure, we'd like to study, say, a generating functional or a Laplace transform in the field, moment generating function, which I define like this. Sigma of f is a test function, is given by this integral. And I've actually not taken this rescaling into this generating function. You can always put it back afterwards. Then you can use a well-known trick of completing the square in a Gaussian or translating the Gaussian to get rid of this exponential factor here, right? So you can shift the Gaussian. So the integrand will be shifted by phi plus CF. C is the covariance of the Gaussian measure, which in this case is this Laplacian plus a mass inverse, this Green's function. And we obtain this factor out in front. You look skeptical. No? OK. So let me do this. I've done this shift. And then I write the resulting expression like this. We have this explicit factor out in front. And now I want to see this Gaussian integral here as I write it as an expectation. So we have the expectation of the perturbation functional shifted by this field CF. And of course, once you know this, this generating functional, you can express the susceptibility, which I'm interested in terms of this. The susceptibility is the sum over the two-point function. So if you differentiate twice with respect to f, you get two fields downstairs. And if you then you substitute in a constant test function, which gives you a sum, then we have two sums, and we need to divide over by one sum and get this formula for the two-point function. And also note that I've put in this rescaling factor back, since I didn't put it into this generating functional. So again, let me emphasize, nothing has happened. I've just rewritten this expression in kind of an arbitrary way in terms of two new parameters, which is the mass and the z0, and I don't know what they are. You can go even further and define this expectation of the shifted Gaussian, or if you like, it's a convolution with the Gaussian measure. I'm going to call that z sub n. So z sub n is the convolution of the integrand z sub 0 with the Gaussian measure with covariance c. So in other words, it's this expectation where phi is kept fixed and sigma is integrated with respect to the Gaussian measure. Oh yeah, this is a notation I'm using for the convolution. It's not an it just adds this field zeta and takes the expectation. So then this has a name, and you can write this susceptibility. You can see what it is in terms of this Zn and this factor. The first factor you can calculate. It'll just give 1 plus Z0 over m squared. And the second factor also has a constant depending on Z0 and m squared, and the second derivative of this functional Zn. Now again, I haven't said what Z0 is and what m is. So nothing has happened to this point. But so this is the point of departure for what we'd like to understand, which is how we'd like to understand this functional Zn. So in particular, if we can choose Z0 and m squared in such a way that this Zn is small, then we have an expression for the susceptibility. And in fact, we're going to achieve such a choice such that the second term, in fact, will go to 0 in the infinite volume limit. OK. So now, of course, a difficulty in understanding this Zn here is that this is an expectation with respect to a free field. There's a mass in it, but we like to understand this for any value of the mass. We don't know what the mass is at this point. In particular, we want to approach the critical point. It will turn out that to do that, the mass will go to 0. So we don't know what the mass is. And if we set the mass to 0, then this covariance has very long-range correlations. Not summable, far from summable anyway. So that's the key difficulty, of course, how to make sense of this expectation. And well, to achieve this, let me recall some basic fact from probability theory. First, that Gaussian measures are well parameterized by the covariance rather than by the quadratic form that appears in the exponent. And that they have this semi-group structure that if you add two covariances, and again you obtain a Gaussian measure, of course, and that this Gaussian measure is the convolution of the two original Gaussian measures. And, or said in a different language, that if you take two independent Gaussian fields with covariances C and C prime, then the sum is again Gaussian, and the covariance is C plus C prime. And it turns out this is a kind of algebraic property that remains true if you look at fermions. It still makes sense. Now, we want to use this property to decompose the free field, which is kind of singular, and, into sum of fields which are all much better behaved. So equivalently, we decompose the covariance, the green function. And so all of this will be on a finite torus. And the side length of the torus will be taken to be L to the power n. So this is a sequence of finite tori whose side lengths increase exponentially. And I'd like to write this green function as the sum C1 up to Cn of covariances with good properties. The properties I'd like, first of all, we need Cj to be we need each Cj to be positive definite. This is a triviality because otherwise they're not covariances of a Gaussian measure, right? So we certainly need that. Then secondly, and this is the non-trivial requirement, we like these covariances to have this finite range property in the sense that that correlations vanish if the distance between the 2 points is larger than, say, a constant times L to the j. Now, it's actually not a triviality that you can find such decompositions that achieve these two properties simultaneously. The positive definiteness is kind of competing with this finite range property. You could always do this if instead of finite range you ask, say, for exponential decay. But we really like the finite range property because, using the finite range property, you don't need a cluster expansion anymore. You can use independence. And the story is complicated enough, and this is a nice feature not to have to do a cluster expansion. But the good news is that you can do this. And in fact, this is kind of an interesting story of itself, I think. You can use the wave equation to construct such decompositions in a very general context where you have a uniformly elliptic operator, say, and also in the discrete case, there's a version of this. Yeah, so maybe let me say as a side remark, if you have, say, the green function on Rd, 1 over x to a power, which is radially symmetric and homogeneous, then you can exploit this radial symmetry and homogeneity to just write down such a decomposition. But we're on the lattice, and we have neither homogeneity nor radial symmetry. So we have to do something different. And it turns out you can use the wave equation too. Anyway, so then in addition to these properties, we like these covariances to decay, just like the original Green's function. That's a discrete. That's a finite difference. That's a no, it's not unique. Very much not unique. Yeah. But it doesn't. All that matters for this is that you can that it exists, right? We don't need it to be unique.
What is BGM?
Oh, this is Brydges, Guadagni, and Mitter. So they gave the kind of first construction of something like this, and I gave an alternative construction that applies to a very general class of operators. Well, I don't think so, not that I know. This is for the discrete case in particular, right? And probably anyway.
In the spectrum terms, are the spectra of these operators different or they intersect?
So in Fourier space, they intersect, yes. Yeah, because otherwise they can't be localized both in Fourier space and in real space by the uncertainty principle, right? So they're not local in Fourier space, but local in real space. How can you, and an important point is that, basically these covariances are independent, or they're all the same, no matter what the size of the torus is, until you reach the last one. So you take a bigger torus, you get more and more terms here, but the first ones basically don't depend on which torus you're looking at. So how can you make use of such a decomposition? This was understood by Wilson at a kind of heuristic level, who basically I guess who I may basically paraphrase as follows. If you want to look at the first convolution, remember this funny symbol theta is the convolution. You want to look at the first convolution with the covariance C1 of the initial density. Then you may proceed formally and just maybe interchange sum and integral and try to compute those moments, which are Gaussian moments, which you can compute, and then rewrite it into a form in which it originally looked. And what you see is that there's a part that looks very much like what you started with, except that the coefficients have changed. And that there is a part which, but then you also have like infinitely many more terms, this formal level, which are, however, OK, so first you have infinitely many more terms if you do it this way. But these terms are all either more non-local or higher order. And so these, by local I mean, so this is a monomial valued at a single point, and you more non-local, you may have like a field at one point and a field at a different point. And I guess Wilson's key insight was that for critical phenomena, these non-local or high-degree terms don't matter, really. They're irrelevant in a sense. And well, many of you know this very well, but let me still say, let me still give an example. So let's take dimension 4. The covariance decays like L to the minus 2j. So in particular, the field is typically of size L to the minus j. So if you consider, say, a field raised to a pth power and summed over a block of size L to the j, which is the natural length scale here, then you see that this grows, and then you compute its size according to its heuristic. You see that it grows if the degree p is small, and that it decays if the exponent p is large. You can do similar heuristics for like terms having gradients in them and so on. And what you find is that according to these heuristics, the only terms that are either marginal, so neither growing nor decaying in this heuristic, or relevant, growing, are these three terms up to symmetries, which allow you to exclude other terms. So then Wilson's argument is basically that all the other terms are irrelevant and will, if you keep repeating this procedure, will decay and not play a significant role to understand critical phenomena. So the only relevant term here was the phi squared term, and I should normalize its coupling constant. Let me not go into this. So I rescale it a little bit and call it mu instead of nu. And then what this leads to is this kind of dynamical systems picture. Coupling constants given at one scale give rise to new coupling constant at the next scale. But then there's also this kind of mysterious remainder, which I wrote formally like this. And so this picture, basically, the picture of Wilson is that there are these finitely many expanding or marginal directions, which you need to understand well, and that all the rest is in some sense contracting, so you don't need to understand it very well. Yeah?
Of course, there's always this problem that phi is unbounded, so the remainder term may look very small, but for very large values of phi, it might still cause some difficulty.
Well, yes, so I come to that in a second, and I won't be able to say much in the time I have in this talk about what this k is. But of course, there's numerous difficulties in getting good control of this k. So, well, you brought this question up. So, what is this k? What can you do about this? And then that's of course at the heart of the matter here. But then there's also the more the softer question: what can you learn from this dynamical system about the original problem you started with, right? So as I said, I won't be able to give a satisfactory answer about what this k is. Let me say that what we'd like to have is a kind of a Taylor remainder formula. So instead of expanding everything out here, we'd kind of like to have like a second order approximation plus a remainder term, right? This is what we'd like to have. However, if you write down a naive formula for the remainder, then there's no way to control it in the infinite volume limit and so on. So you have to somehow make use of so if we go back to Wilson's insight here, you kind of have to make use of the fact that if you're very much looking at very much non-local terms, that they're much smaller, that they're decaying. So what you need is a much more elaborate version of Taylor's formula. And let me write it like this. So there's a sum over regions in space. There's a part that we'd like to know explicitly. That's kind of second order. And there should be a remainder term. Such estimates, so we're not reinventing this here. There's a long history of such things, and in particular for the two-point function of the weakly self-voiding walk, this was developed independently by Brydges and Slade, and we're making heavy use of this. And it leads to such a replacement for this kind of Taylor formula, in which this remainder has a locality structure, and it's partitioned into different regions of space, and the certain regions are independent of others. And if you take a torus large, then if you look at a selected region, that basically won't change. And so you can do this, and you can control the infinite volume limit. As interesting and key as this is, let me say a few words about the other aspect that you need to understand, which is what you can learn from this system once you understand how to control the remainder. And so at least if you're looking at a dynamical system that's hyperbolic in the sense that all directions either expand or contract, then I should have started a little bit earlier. Let me say first that 0 in this parameterization is a fixed point of this dynamical system. So
don't have 0 directions.
I'll say a bit about that in just a second. So 0 is a fixed point of this dynamical system, and so we like to understand this dynamical system in the vicinity of this fixed point. Now, if this dynamical system were hyperbolic, then this is a well-known answer, and there is the local phase portrait near a fixed point is well understood. By the stable manifold theorem, there's a stable manifold which defines the domain of attraction of this fixed point. Now, in this case, this dynamical system is not hyperbolic. It has, in fact, two directions that are marginal, that are neither contracting nor expanding. One is the kind of field strength, and the other one is the g to the 4 coupling. And in this case, it turns out that this picture remains true, more or less, but it's much more subtle. In the case where you only have one marginal direction, there's a beautiful trick of Bleha and Sinai to construct such a kind of stable manifold. We proceed a little bit different here since we have two marginal directions. But the point is that this picture roughly remains true. Now, in the usual heuristics of the renormalization group, the stable manifold, the domain of attraction of the fixed point, corresponds to critical points or critical theories, while unstable trajectories that eventually go away from the fixed point, are subcritical theories. Our implementation of, so I should say that we are really interested in studying subcritical theories. We're interested in the approach of the critical point. We're not sitting at the critical point, right? We want to see how the susceptibility blows up as we approach the critical point. So we're in the second case, where we'd like to understand it sufficiently uniformly that we can approach the critical point, of course. So it turns out that we don't like these trajectories to go very far away from the fixed point. So we proceed slightly differently. Rather than moving the initial conditions away from the stable manifold and following trajectories that eventually move away, we perturb the dynamical system a little bit to correspond in a certain sense to a massive Gaussian. And then we follow stable trajectories for these massive Gaussians. So we always remain close to the respective fixed points we're looking at. On the other hand, we also like to understand how things change if you approach the critical point. So in this picture, we'd want to understand how these mass-dependent stable manifolds change with the mass. And it turns out there's various technical difficulties in doing this. So we follow a kind of hybrid approach in which, to study the change of the stable manifold, we actually do change the initial condition slightly away from the critical trajectory, but we only do this in finite volume, where we only have to follow a finite part of these trajectories. And if we move away sufficiently little, then we'll always stay kind of close enough to the fixed point. In fact, we only compute derivatives orthogonal to this stable manifold, in a sense. So this allows us to also, in the massive regime, always stay close to the fixed point, in a certain sense. And I'm almost done. Let me say a few words how this looks, or how you can see these how the result emerges at some level. First, let me recall the somewhat complicated-looking formula I showed earlier, which I just wrote the susceptibility as this explicit part plus this perturbation here. Right? This if I may recall, this formula simply followed. Well, there was nothing happened in this formula, right? I just introduced these artificial parameters z0 and m squared, and I could just, by redefining variables, I arrived at this formula. Now, if we, right. So now we consider this m squared as fixed, right? We fix some m squared, and then we want to understand what do we know, and we can find. So if we fix this parameter m squared and this parameter g0, we can use this picture here to find parameters z0 and nu0, which are the parameters of the gradient phi squared term and of the phi squared term, so that this remainder goes to 0 if we continue following this trajectory. So in other words, in the infinite volume limit, the susceptibility will be only given by the first term. Of course, this is not so useful yet, because we don't know. Well, we want to know how these parameters z0 m squared are related to the original parameters. Otherwise, this formula is not. It doesn't say very much, right? It's just. Sorry. So, and for that, we, as I indicated previously, we look at these derivatives orthogonal to the stable manifold in finite volume, and you can compute them and find that they depend also on this parameter m, this artificial parameter m, a certain way. And putting both of these results together, you can then find a differential relation for the susceptibility, which you can solve to see the behavior as the critical point is approached. So how do you, and this is the next slide is going to be the last slide. How can you understand this? How can you compute this derivative? And so let me just give some very brief indication to see to give a flavor of how these things arise. Let me just look at a very small part of these recursion relations of this dynamical system. Let me drop everything that will eventually not matter. then what's important are these two equations. The first one, G, let me recall, is the coupling constant of the phi 4 square term. And it decreases like this. But we proceed, and of course this is a very well-known equation. One difference in what we do is we have m-dependent coupling constants here. So these coefficients here actually sum to exactly 8 times this bubble diagram, the expected intersection time of two independent simple random walk with killing rate m, which blows up like log m. So, and if you solve this recursion, you find that its limit, g infinity, is asymptotic as m goes to 0 to 1 over this bubble diagram. So it has this, so it goes to 0 like 1 over log m.
So what are the beta j's?
So these beta j's are kind of bubble diagrams that correspond to the massive Gaussian.
At scale j.
Yeah, at scale j. So they correspond to the massive Gaussian, so we get the bubble diagram in this way. And then the other factor, this 1 minus a quarter beta j gj, can be written as gj plus 1 divided by gj to 1 quarter plus a small error. And this would be a good form to iterate this equation, right? We don't iterate this equation, but we iterate its derivatives equation. But never mind, if you do this, you find that you get something like g infinity to the 1 quarter, which is this log m to the 1 quarter that appears here. OK, I think I've used up all my time, and I think maybe I'll stop here. Well, if you're in low dimensions, there's more directions that grow. So what's conceivable to do is where you could conceivably still find a stable manifold, but it's not, it doesn't correspond to the cases you may be interested in, right? So in low dimensions, say in 3 dimensions, G is growing, right? So yeah, well, you could still study the Gaussian fixed point, but there's going to be a second fixed point, which is going to be the one of interest. Yeah. Oh, it's simply that this supersymmetric formula becomes nice if you have a continuous time, because you can write the resolve or the green function nicely in terms of continuous time random walks. But if you have a discrete time walk, there's another factor, and I guess presumably you could do something, but just simpler like this.
Is there a way to avoid the supersymmetry if you didn't want to use it?
Well, I guess there's work by, I mentioned this somewhere, Iagol, Nitzna, and Magna. I think they don't use supersymmetry. They study some kind of version of the Edwards model. It should be closely related to this. So presumably, yes. I guess John might, you probably know something about that, right?
Well, I guess they split the 5/4 into quadratic times the next field, and then they just treat both fields as, rather than integrating over that field, they just do it all together somehow.
Yeah, so I don't know. Yeah.
So I guess when you derive your recursion formula for the gj plus 1 in terms of,
Yeah.
you use some kind of cumulative.
Right. Kind of.
So in which way can you now avoid cluster expansions by choosing these very special covariances?
Well, so this is, well, so let me only say a few words about this. I'd be happy to say more maybe after the talk at some point. Basically, sorry, what? Well, okay, well, it was, okay. Basically, so what you'd like to do is keep the interesting part in the I and the non-interesting part in the K. Now, assume you already knew what the next I would use. So now you want to take an expectation of this expression, right? So to get, or this convolution to get the next. You want to write it in the same kind of way. Assume you already knew what ij plus 1 was. Then you only needed to take the expectation of this kj, right? And kj has the property that it factors over connected components. So x is kind of a polymer. It's a union of blocks of size L to the j, and it can have connected components. And k factors over these connected components. So since we have this finite range property, the expectation factors over connected components. So then you can make use of, so this is not the end of the story, but this is a key ingredient that you can use, this independence property, that these k's over different connected components are independent. You can evaluate them separately.
Otherwise, you have to do a cluster expansion.
Yeah. Otherwise, and this is what so there's a closely related. So this technique grew out of the treatment of the dipole gas by Brydges, Yao, and they used a cluster expansion.